Actually, it seems that we have covered many examples from the textbook. And I will be introducing more examples today. So here we go. And those examples were presented in the classroom in the previous years. Right now, they will be shared through the computer monitor. Okay, yeah, the sharing sounds okay. Now, adjust the window size, etc. Yes. So today, our examples. We have many very easy and moderate examples today. So the easiest one starts with how many kilobytes exist in, or how many bytes exist in 24 kilobytes. And again, I need exact numbers. They are given. It's simple, like last week's first problem, simple multiplication problem. Definition problem, RAM, and how is it used? So these examples are also a kind of transition from the assembly programming to the hardware. Hardware will be implemented starting next week. Actually, next week you will have your online midterm examination as well. So the hardware topics will not be included in the exam. Don't worry about that. So those examples also reflect some major aspects of the hardware as well. And these are, for example, there are buses in the computer system. And up to now, we have been utilizing some kind of hexadecimal numbers and some commands related to transferring some data in or out of the registers, okay? How are these implemented? Of course, they are implemented electrically through the special bundle wires, a group of wires called buses. And there are three types of buses in the main computer, which you had already learned it or experienced or observed or seen it in the Computers and Programming 1 course, okay? There are three buses. Our segment addressing, physical addressing is related to address buses. So up to now, the physical address, the concept of physical address is on the circuit board, 20 different conducting wires, each carrying a logical information, 1 or 0, okay? And of course, data bus is also represents the data stored in the register or read from the register. Again, requires a special other group of wires to transfer this information. So definition, PC program counter, and the usage or summary or brief explanation of its usage is given here. It stores the address of the next instruction of the program or the code. So there's another chip required to decode or understand the information in that or in any assembly code. Okay, you remember the mnemonics in assembly code, 3 or 4 letter short forms of the commands. They are expressed in machine code. Machine code is transferred to some kind of other logical information after passing through another chip or a group of chips called instruction decoder. So according to the machine code of all instructions, this chip supplies some signals to other hardwares to decode them before execution. So As an example, okay, this is the, let's say, one of the, okay, this is the first example or the first command that you have seen in assembly coding. Assigning some value to any register is performed, or one of the ways is performed with move instruction, okay? And up to now, we have seen this instruction as the information given on the screen, okay? Then from now on, we will translate this information to hardware. How come this information is processed, for example? So if this instruction is written on your code, okay? The instruction decoder is that's a digital circuit with clock, okay? Or it's a synchronous uh, clocked logic circuit, so that it brings the contents of register AX to internal data bus, and then copies. Copy means loading the flip-flops of the associated register, the internal data bus into the register BX, okay? So what's happening in this simple move command is, on the hardware basis, on the very low level, is transforming electrically the contents of AX to the bus and copying the contents electrically or charge in the charge wise to another register. Well, that register is actually an array of flip-flops. So you load some value to the associated flip-flop. So that's what's happening. So these examples are continuing, okay? And there is a 6-bit binary conversion to decimal to hex, but beware that we will not be using 6 bits or 3 bits or whatever. We are using 8 bits or 16 bits. So everything should be expressed as 8-bit form, okay? So remember, this is not allowed in your examination. You have to write in this form with 8-bit expression. Of course, there should be no hyphens or other characters, just zeros and ones in binary notation. There are other, let's say, simple or basic examples of hexadecimal addition, which we had already performed this, and emulation of this. Okay, some people have very recently joined our sections due to some problems in registrations or approvals or etc. They may have missed the first 2 or 3 weeks, etc. So those examples are for them to reveal the basics again. So some of you guys may be bored about that, but it's a good way to practice. So I know everybody's now an expert on emulator 8086, so you are very familiar of those kind of screens on your computer, and this is how it's done in the simulation world to add two 16-bit hex numbers. Another example specific to stacks, and there are some values already stored on these segment registers, like stack segment or stack point register, and our usual most popular register AX, okay? So if we push the contents of AX onto the stack, it asks what happens, but we had already done this, including with an illustrative example before, okay? So this is the basic flowchart expression of the previous assembly code. I really recommend you to use flowcharts, okay? Because you will be receiving questions related to online flowchart drawing example that I had already given as a homework. Unfortunately, this section, only 25% of the classroom have submitted requested homework, okay? Which seems to me very low percentage, okay? As I told, the homeworks in these weeks before the midterm examination will be related to your exercise, plus the same type of examples or codes will appear on the midterm. In the midterm, you may see a question saying that refer to your previous homework and borrow this figure and answer this question accordingly, for example, okay? So if you have not done the homework, unfortunately, you may not get any credit in the midterm examination. That's the, I think, second week that I'm repeating this information or important aspect of the midterm. So please be more eager to do all of my homeworks as best as you can. For example, some people could not do all the 4 problems, but made 3 of them. Good, because I will select problems that are finished or done or solved and uploaded by the majority of the section people, okay? So flowchart drawing definitely will be an issue which will be required in the midterm as well as in the final examination. So there are some remarks. You cannot copy an immediate data directly to stack segments because the emulator gives an error. You have to write the data to some general registers first and then copy the contour segment registers. So this is like operational constraint, okay? But not all the segment registers are like that. For example, SP or stack pointer register, you can directly write any data to it immediately. So we have to change it indirectly via BX, for example. That means we don't, we use BX as a dummy register to store the data and then copy the same data to stack segment register. So instead of 1 line of code, we require 2 lines. Well, that's inevitable. So this is again, for the latecomers, important topics or issues about pushing the contents of 16-bit registers into the stack by using, of course, little endian formats. So you see the result or outcome, and high byte goes to the high address. High address is one upper, at the upper level compared to the low byte. And here is a kind of simulator screen. Well, and it can be omitted at this moment for your self-study. It's very easy for you at this time, but if you have some difficulty in running in the emulator, you can check with these guides or answers or window images or screen images, etc. Another example question asks you to repeat the previous example by the following code. And this code, okay, for the previous code was related to storing some values to the stack. This example has a few more lines added, okay? So basically what you can read is you are storing some data and pushing the value of the general register AX to the stack. And then you add a mathematical operation and then you push the result to the top of the stack again. So actually, this is 2 or 3 steps more in flowchart drawing, but you can draw the flowcharts, okay, and you can also convert from assembly code to the flowchart very easily because each line corresponds to simply one block, except some decision uh, moments, etc. So it's very easy to convert from and to between assembly code and flowcharts, drawing graphical representation and vice versa. So there are some illustrations in the emulator screen about the code or realization of the code and the appearance in the memory. So this time we have some data and then we have another data which is the result of the addition operation. So they're indicated on this slide accordingly. Another example, you are expected to write a program whether a given number in BL is a prime number or not. Okay, so that's a very nice. Actually, this is like a laboratory exercise drill. Okay, in the midterm, I do not plan to give you long program writing. Rather, I plan to give analysis examples. Analysis means you have the codes, for example, the example codes in the emulator. Then I ask questions about specific parts, etc., writing or drawing its flowcharts. So this is like this is also an analysis. So you have the code, then you try to understand the code or express the code in usual terminology or usual English language, usual literature writing, whatever, explanatory writing, okay? But this is a synthesis example. You write a program, whether a given number in BL is a prime number or not. What's the prime number? Prime number B means that it's only, well, it will be defined in the next slide, but that's okay. The result should be a Boolean variable stored in BH. That means if a number is a prime number, okay, if number in BL, low byte of B is a prime number, then BH should be 1, for example. The whole register stores Boolean variable. If not, it should be 0. So let's have a look at the definition of prime number. Okay, they everyone knows the definition. It's a number which is divided only by itself and by 1, nothing else, no other number else, okay? So if we divide a prime number in the memory, okay, that's the logic of the program with 2 or 3, etc., we will have a remainder, okay? Definitely. And we have to check that remainder exists or not, starting from 2 up to 1 less the number, okay? So we exclude 1 and the value of the number, and we check with all the numbers. Okay, that's one way of writing the program. Of course, there are more efficient ways to do this, but in the simplistic sense, we have to check, we have to perform some divisions and check the remainder. That's it. So div command is a very useful command for testing. Also, we can use I there. Okay. The given number in BL is a byte variable, so our range of numbers will be from 2 to actually 254 decimal, okay? Because we are not checking 1. And, well, actually, we don't check whether 0 is a prime number or so. 1 is definitely prime number or not, it can be argued, but we assume not, and they are not considered to be prime numbers. These are our assumptions. We have to state the assumptions. So if you write any program, you have, in the beginning of the program, you have to state your assumptions, okay? That's not for our midterm, but it will be useful for you for the final and for your projects and laboratory assignments, etc. All your electronics or computer engineering programming career in your life. So the flow chart of this program could be as follows. Okay, so you notice that I not only give the assembly code but always present the flow charts, because flow chart drawing is very important, and you will be responsible in all your examinations and homeworks. You start to the program or subroutine, and you give some message saying that, hey, you enter, this is a program to give whether a given number is a prime number or not, etc. So there's a message on the screen to inform the user of the programmer. And it will say that do not enter 0, do not enter 1, because they are not considered as prime numbers. If you enter those things, the program may include some kind of error loops or interrupts, etc. If everything's okay. So it's not explicitly shown here, okay? Error loops and those kind of details, etc. Defining interrupts on the screen, etc., are not shown in this flowchart, okay? They are, okay. If we show, then this flowchart will be more and more complex, couple of pages long, okay? So for clarity, they are all included in that rectangle at the moment. If everything's okay, message is okay, user is ready, entered some numbers, etc., we assign or clear some registers or assign values to registers. AH, BH. BH, you remember, means, or it's an output register. It should be 0 if this number is not a prime number, if this value is 1, if this is a prime number. And we copy BL to AL because the numbers stored in BL, okay, should be copied to AL for division operation, okay? We also have to set some kind of counter because we will be starting to test the divisions remainders starting from 2 up to the number which is 1 less than the given number. So counter CX register is set to the value, okay, of the given number. And then it's decremented by 1 because this is the maximum value which will be tested, okay? And this decrement also is useful for the return of the loop. And then we copy BX to AX, okay? Because right now we have to, since BH is 0, BX actually carries the BL, the number. Sorry, my mistake. Forget about my last sentence. Now the counter is set, and that through the arrows, we check whether the counter reaches 1, which is the last item. If it's 1, then all the checks are complete, okay? That means we got down to 1 and we could not find a remainder, zero remainder. So that's a prime number. If the counter is 1, that means we have found no numbers which can divide that given number. If CX not 1, then we continue the loop, and the loop continues to divide AX with CL and check AH, which is the remainder. If AH is 0, yes, then the given number is not a prime number. 0 is copied to BH, and the program should exit. If the AH is non-zero, that means remainder exists in that division. So that means it's not a, it may be a prime number. We have to check the next number till the end, okay? And we copy BX to AX, uh, and then continue to decrement the counter and continue to divide till CX reaches to 1. So at any time, there's a zero remainder. That means our number can be divided by 1 and itself as well as that number. So one failure of that test results in to exit the program. Well, not much time left due to Zoom recording, so I will terminate this session and we'll be starting the next session probably 5 minutes past